So we are working on this example to use the second derivative test to classify the critical points of this function as a local or global maximum or minimum or a saddle point. So looking at the form of the function, we know that that this function is continuous and differentiable everywhere, being a polynomial function. So first let's just go and look for critical points. So for that, critical points are the points where the partial derivatives with respect to x and y, we mean the first partial derivative, they are equal to 0. Each of them has to be 0 or they don't exist. All right, so first let's go for the partial derivative with respect to x. So here we are. So when we are differentiating this function with respect to x, let me not do it like this, then we know that 6 and y square are a constant, so the derivative is 1. X cube, we'll just use the power rule, and this will become what? 3 times 2, that is 6, times x square. So this becomes 6x square. Okay, and then after that, you see this here, that is, this part will be treated as a constant, so the first partial of that part is equal to 0. So this is our df dx. Now let's go for df dy. All right, so for df dy, let's just work it out here. So in this case, this portion is constant, y square, the derivative would be 2y. So when we multiply 6 with 2, we are going to get 12, and this is 12xy, and this is a constant, so the derivative is 0. All right, and here just by power rule, it will be 4 times y cube. 4 times 3 is 12. So in other words, it will be 12 times y cubed, right? So we got this quantity equal to our df dy. I'm sorry, I didn't change that portion. Okay, so now what we will do is, we see that these partial derivatives exist at every point. Now what we have to do is check for the points at which both of them are equal to 0. That is, this is 0 and as well as this quantity is 0, right? Okay, so if we look at this portion here, this quantity equals 0. So one place that this will be equal to 0, where both x and y's are equal to 0, that we can just see by observation, right? And then we get y square, 6 is factored out, y square minus x square equals 0, or in other words, we have y square minus x square equals 0, and we can factor it as y plus x times y minus x. Okay, so we will do that. Y plus x times y minus x, that equals 0, will make it 0, right? Okay, so then what happens is that these are the places where this first derivative with respect to x is 0. That is, either I am at 0, 0, or I have y equals either plus or minus x. Okay, so these are the places where the first partial derivative would be 0. Now let's go for the second partial derivative. So there, what we get is that we get here, first of all, 0, 0 is going to satisfy this equation. So we got at least one critical point. Now let's say we can factor a y out, And when we factor 12y out, what shall we get is x minus y squared, right? And that equals what? That equals 0, right? So as a consequence of this, we again have this will be 0 at y equals 0, including, I'm writing points and equations in the same line, but we are just, informally writing our points here. So this is just a point, or at the place where y square equals x. So y square equals x where at 1, -1, and 1, +1, right? Am I clear? Good. So let's just take the portion in which we have both the equations becoming 0. So one of them we get as 0, 0. And if we collect the other points, you can see right here, we had actually y square equals x, and I just went like biased in this way. So we had to, because y square x is going to be satisfied by many points, but y square equals x is not necessarily going to make this 0. So what we did was, let me again specify here how we got those points. We needed y square equals x and y equals plus or minus x, right? So if you substitute this value in here, what you will get is x square equals x, right? Okay, so for x, the two values that we'll get from here is, let's just do our basic algebra again. Okay, that is, here we got minus x equals 0, and that will mean x times x minus 1 equals 0, and that will mean x equals 0 and x equals or x equals 1. All right, so we can see that here, so which will mean y equals what? If x is 1, y is 1, and if x is if x is 1, yeah, y is plus or minus 1, and even if x is -1, is the same. So there's so much to be said here, and you can see that the points that we are extracting from here are, okay, 1, 1, and then 1, -1. Okay, so these are the three critical points that we have. Now we have to apply the second derivative test. So let's just quickly recall what our second derivative test is. So here what we are going to do for the second derivative test for function of two variables is that we are going to compute this quantity by multiplying the second partial with respect to x and the second partial with respect to y, then this mixed partial at a critical point. So if this quantity the discriminant is greater than 0 and the second derivative with respect to x is greater than 0, then we have a min. In case the discriminant is greater than 0 and second derivative with respect to x is less than 0, then we have a relative max. If the discriminant is negative, then we have a saddle point, and in case this is 0, then this test is inconclusive. So let's just recall these points and obtain our second derivatives. Okay, so here our first derivative with respect to x is 6y square minus 6x square, which implies that if we take the second derivative, then we get d2f dx squared. All right. And here this part is a constant, so what we shall get is simply negative 12x. All right. And we can also obtain right at this point that what the second mixed partial will be, because in this case all the conditions are satisfied. So what we have is that the order in which we take the partial derivatives, it doesn't matter. So when we are differentiating this with respect to y, because that's what this means here, what are we going to get? This y square will be differentiated. Differentiated becomes 12y, and this part is a constant, so we just ignore it, right? And then we are simply going to take the second partial derivative with respect to y now. So we got 2 here, and so we are differentiating with respect to y, so this part will become a 1, and here y cube will be reduced to 3y square, which times 12 is 36y square, right? Okay, so if we calculate our discriminant, that is this value, which is going to be this second derivative times this one, that is with respect to y, and then minus the square of this one, and we did not obtain the dx dy part here, all right, because we know that in this case the order will not matter whether we do dy dx or dx dy. Okay, so this is what we have. So if we do this, that we calculate this value at, say, or just let me write it differently. So let's first calculate this value at, and let me just bring our critical points down here again for an easy visibility, right? So if we calculate it at 0, 0, then what this will be, actually it will be a good idea to do one more thing, that is just write the values of these. So this is negative 12x, right? And then the second derivative with respect to y is negative 12x minus 36y square. And well, yeah, that is in that order. Then minus this thing, this second partial, dy dx is 12y, so we'll simply square it, right? So 12y squared here. So at 0, 0, this will be how much? 0 for this. So for this part, we are getting an inconclusive situation, right? Okay, so next would be, let's bring in 1, 1. So if we do this, if we take this quantity and put x is 1, so this is simply 1, 1. This is 1 square, so would be 1 again, and this is the 1. So if we calculate this value, what do we get? We get a positive number here. So this tells us that we can do further investigation, meaning thereby that let's just see what this value is at where 1 negative 1. Okay, then if we compute this value at 1 negative 1, how much is it? This will become negative 12 times 1, right? And that is simply going to give us negative 12, which is less than 0. So we are going to get a relative max here. Okay, and you can see that the other point is 1 negative 1. So x coordinate is the change, only the y changes to negative with the same value, and all the values here, the way they involve y are only in terms of squares. So what would happen is even at even at 1 negative 1, we don't have to go in detail, and I'm going kind of in little detail. That is, you shall still see that this value is 144, which is less than 0. And of course, and here even I wrote 1 negative 1, even though I was working with what? 1, 1 there, because it didn't really matter. X is the value is negative 12x and x is the same here. So anyways, if I change it to negative 1, y is absent there, so the value will not change, it still remains negative 12. So what we have again, even at that point, we have a relative max. All right. Now, at 0, 0, remember we had an inconclusive situation. So let's go ahead and just check what is it going to do at 0, 0. Now we don't have any formula. We just have to look at the function, just thinking about it. And so I'm just going to present to you the way I thought about it. All right. So we have this is the function that we are looking at. Okay. So generally, I just start looking at it through different paths and see how it's behaving locally at that point. So what happens here is that if you did this, that say intersect this with y equals 0 plane, all right, which means that we are looking at it in the xz plane. Then what happens in the y equals 0 plane? This is going to become simply negative 2x cubed. Okay, so what happens here for this one, for this path at x equals 0, you can see that this is simply, let's look at it graphically. I mean, this is only a function of one variable, what we are looking at. So if you look at this graph, and of course, the graph in 3 dimension will be a cylinder, but if you notice this here, what we get is a saddle point at 0, 0, right? Okay. And notice this, that this graph, if we just go for z equals negative 2x cubed, that will be just a cylindrical sheet. Okay. Now say we intersect the, this surface with x equals 0, then what will happen is, so here would be 0 y, and this is going to change. Okay, so when x is 0, this whole thing will become 0, and what you shall have is negative 3y to the power 4. And here you can see this is an even power. I mean, I can go and sketch it, but this is an even power. This is a negative sign. So we are going to have a min at y0. So if we go along this path, we see a min. Here we see a saddle point, and we can just go ahead and check other things. Sorry, other paths. It will be showing different behavior. So we are going to see that 0, 0 is what? 0, 0 is a saddle point. Okay. So we have classified all the points. Okay. And if it is, if I'm writing this on a test where I have to show this analytically, we are done. But let's just go ahead and quickly look at it in a graphical fashion, in a way just to verify our answers. Okay. First I have to fix this, that this is saddle point. Okay, is a saddle point. Okay, all right. And then let me just look at the expression so that I type it quickly when I go to a graphical situation. Okay, so I would just do this. I can ask for Geogebra 3D in say in Google, and here I'm just, let's just go ahead and not have this plain, and our function is, what is our function? That's 6xy square and then minus 2x cubed and then minus 3y to the fourth, right? So this is our graph, and we can do this. We know that 1, negative 1, and then 1, 1, and 0, 0 are our only points of interest. So we may do this, that just restrict this, say, between 3, 3, negative 3, negative 3, negative 3, 3. All right. And here we can just go say negative 10, 10. Might show us a better graph. Let's see what it shows. Yes, so we can change the color. Okay, but here, I mean, like this is too transparent, but you can see this here, that this and this are the two maxima, or two local maxima. Global maxima it won't have, uh, because of, first of all, because when it increases with in the positive territory for x and y, or so for the z values, it will just go on increasing indefinitely, and same way for going to the bottom. So these two are relative max, and here at 0, 0 we have a saddle point. Now let's go ahead and look at it in MATLAB as well. So here I have pulled up MATLAB, and in MATLAB we have been using LiveScript. So this is, we will just click for new LiveScript. Okay. And that is going to bring this window for us. And we have a symbolic feature available here. So we'll say that x, y are symbols. Then we will define our function of x, y as 6. Now, you know, here we have to go the old-fashioned way. That is, we have to put a star for multiplication. So we got 2 times x cubed, all right, minus 3 times y to the power 4. Okay, now MATLAB in the version 2020 and later at this time, you know, this changed the command to fsurf. So we want to draw this surface f, and we already know that our region of interest is negative 3, 3. And to get the graph really smooth, uh, we may change the mesh density. In the sense, this mesh density is, it will give you, will tell you how smooth the graph is. That's what I can say in plain language. And then 35 is the default value. Let me put 60 here. And then what I would do is, just like the earlier demo, I'll restrict my axes between -3, 3, -10, and 10. Okay, now we will press Control Enter to see the graph. And here is a graph for us, right? Okay, and looks like I messed up something. What have I messed up? We got -3, 3. So, or I typed something incorrectly. Okay, what did I type incorrectly? Right here, this should have been a y square, right? Okay, so let's change that to y square. And now let's see. Yes, here we have the graph that we wanted, right? So we can see that we have these two local max here, and there is our saddle point. If we want, we can draw our lines. Remember that the lines that we got by doing this, that by restricting it to x equals 0 and y equals 0, one of them was a saddle point, the other one was a max. All right, so if you are still staying with me, let me do that in a little bit of detail. So here what we have is that, so first we are going to draw this line or find the equation of the curve that we shall get by restricting this. So we have z equals this value, and this is what I get in the x equals 0 plane, right? Sorry, y equals 0 plane. So you can see an equation of this will be, or an equation of this is going to be, if we write it in parametric form, that if we take x equals t, y is 0, and then z is going to be what? Z is going to be negative 2t cubed, right? So that's one function that we will, that's one of the lines that we will write. And if we go to this one, so here what we get, z equals negative 3 y to the power 4. Okay, and so that means our line is x equals 0, y equals t, and z equals negative 3 times t to the power 4. Okay, so let's just go ahead and draw these two lines in our graph just to stress the saddle point. I mean, we are kind of done here anyways. Okay, so what we are going to do now is that we are going to just plot those two lines in here. So the first thing I will have to do is ask it to hold on to these graphs. Now we are using our parameter as t, so we'll say syms t, and a curve can be graphed in 3D by fplot3. So here we have the x coordinate is t, y is 0, that we are going to have to type as 0 times t, or there is another form, let's not worry about it. And z is what? Negative 2 times t cubed. And let's just go ahead and let t range from negative 1 to, say, 2, all right? And then we will keep our line width as 3 works well for me. All right, let me just move it to the right. We'll bring it back later. Okay, and just to distinguish the color, I mean, I am a fan of blue, so we'll just put a blue here and then say Control Enter. So let's see if it graphs the line in there for us. Okay, all right, it's for some reason it doesn't want to rotate. Here it does. Well, it partially drew the line and I didn't let Z go high enough because I put a negative 1 here. I could have changed it to negative 2. Okay, so then we will hold on to this graph as well and then plot the curve that we have remember the other curve is Z equals negative 3 times y to the 4 with x 0. So here x is 0, y is t, and then what we got is we got negative 3 times y to the 4. Okay, and we can keep the other things the same, and there we are. We got it should graph it pretty soon for us. I don't know why it isn't or it didn't. Let me see. Let me do it once more. Okay, I see the reason it didn't because one moment. I see I left this 0 here in a hurry. I don't know why I did that, but anyways, now it should give us a graph. All right. So y is t and z is negative t to the power 3t to the power 4. And now we have the graph and we can see it much better if we just go ahead and bring it in the plot window. Okay, so here and there you can see you can rotate it in 3D, right? So here we go, the whole graph is there and these are our local max and here is our saddle point. Okay, so anyways, you did not have you were not asked to do the graphic part. We just did the graphs to verify, and I'm going to do this, that I shall post the commands in the text description for the video. Okay,